Welcome back to Valiant PE. Today's topic, statics. Let's go. All right, on this exam, what type of statics problems should we be expecting? What kind of statics application are we going to see on this exam? Well, statics is a first or a second year engineering class, so you can expect that the test authors expect you to be an expert in this field. You should have done it over and over and over by now through a mechanical engineering degree or something like that. So this is a simple topic that they expect you to know really, really quickly. And because they expect you to know it so quickly and really thoroughly, that means you can expect a difficult question. Now, none of the questions on this exam are gimmies, of course, but you're not going to be getting something like, hey, here's a simply supported beam with an applied load, solve for the reactions. It's not going to be something like that. It's going to be a complex problem. There's probably going to be a diagram involved. It's going to make you stare at it for a little bit and think about it, but that's the point. It's going to be hard. However, we know this, it's not going to be so brutal that you can't finish it within 6 minutes. And that goes for all the questions on this exam, but it's going to be hard, it's going to be complex, but it's doable. So what should we expect to see as far as what's a question going to be like? I mean, statics is pretty broad. There's all types of stuff they could throw at you. But what are we most likely going to see? Well, we're taking a machine design exam. So that is a pretty good indicator that we're going to be applying statics to the machine design field, probably some type of machine component. However, it's not just going to be some simple component. It's going to be probably a pretty tricky one or a complex one. So we're going to see a tricky machine component. And that makes sense. We're not expecting them to give us some super simple setup question here. We're not going to get that. We're going to have a diagram most likely, probably maybe even a complex one. You're going to have to stare at it for a second. How the device works may take you a minute to kind of breathe and look through it. But expect that. Expect to have to stare at it. So when you approach a diagram, look at it thoroughly. Don't just jump to quick conclusions. Take a good look at it. The second thing we can expect to see is it's going to be a multiple step problem. And what do I mean by that? Again, we're not going to have, here's a simply supported beam, write your equilibrium equations and solve for a reaction. It's not going to be that simple. Probably we're going to have something else thrown in there, like you're going to have to solve for a stress, or you're going to have to use a stress to find a reaction, or you're going to have to use a shear moment diagram, or a beam table, or you're going to have a design factor or a safety factor that you have to choose or design from or calculate from. All of that to say, there's going to be another step in there that's not statics, and that's okay. We should expect that. And also, probably the key point of what a question is going to look like is how the question is phrased is going to mask the fact that we're performing statics. So masked by question phrasing is going to be key here, or how the question's worded is going to hide the fact that we're being tested on statics. So you're probably going to see something in an exam or a problem statement that's like, you've got this stress, or if a design factor of 2 is desired, blah, blah, blah. So what can we do to mitigate some of these difficulties? Well, the first thing that we should do with any statics problem is a good free body diagram. But for these components, it needs to be very thorough. So take your time, breathe, draw it out slowly, make sure you draw all your reactions in the right spot. Of the entire 6 minutes, the majority of the time I think should be devoted to drawing your free body diagram. Really think that through, because once you write out your equations, you're going to start blowing through them, and solving for sum of x or sum of y is not really going to be very time consuming. So spend your time wisely on the free body diagram. The next thing is, because the authors of the exam expect you to be an expert, they're going to throw a bunch of excess information at you. and they want you to sift through what is and is not needed to determine what you need, figure out what you need and what you don't, and get to the equations quickly. They're going to throw extra dimensions at you, extra words in the, or extra maybe sentences in the problem. They may even give you extra info about materials or Young's modulus or some type of mess like that. The point is that they're looking for you to be able to identify what you need, spend just a hair breadth of time assessing all the information and getting straight to solving the problem. So beware of excess information. Now that's general for the entire exam. They like to do that on lots of problems, but with statics, because it's easy, you can expect it. And then, of course, watch out for tricky answer choices. This is general for the entire exam as well, but again, in this case, because they expect you to be really solid on statics, we can nearly guarantee of the 4 answers, there's going to be the right one, and then there's going to be another one that's probably very easy to get that answer by making a simple mistake. You used a diameter instead of a radius, or you forgot to divide by 2 somewhere, something like that. So just because you get an answer that's one of the multiple choice options doesn't mean you got it right. That's why we really want to hammer your free body diagram. Pay attention, draw it slowly, and draw it well. Now, I'm not going to cover the theory of statics like I do for most other topics, because there are a lot of other videos out on YouTube that are going to do that for you better than I can do it. We've all taken that test or that class. We all know it fairly well. So I'm not going to spend time in the video going over the theory, how to set up equations and stuff like that. But I am going to go through some good examples here. So let's take a look at a typical problem that we might see. Okay, so before we read it, let's just assess what on earth we have here. We've got a diagram, so that's a giveaway. We're probably doing something with statics. It's a machine component, and after staring at it for half a second, it's a little bit of a strange one. We'll get here in a second, but it says this is a self-locking hook. So it's not just a hook. There's 3 components here. There's the thimble, the latch, and then the hook, and the latch and the hook are pinned together. That's a bit of a strange looking hook. Usually I would expect that they would just be a normal hook, like a one big casting or something like that. So this is an indicator, without doing any thought at all, that we probably have a statics problem. But as usual, before we just roll straight into a problem, we've just finished one problem on an exam. We're going to move into this next one. What are we going to do? We're going to do our pre-question ritual, and it just checks us out. It resets us. We're going to do this every time we come to a new problem. We're just going to, step 1, take a deep breath. Step 2, we're going to read the problem slowly. A self-locking hook is suspended vertically by a strong chain. A strap is looped through the hook and a force F is applied as shown. What is the maximum F the hook can handle before plastic deformation occurs at the latch mating face? Assume uniform pressure distribution at the latch mating face. That's here. The hook and the latch are made from a material with a yield strength of 52,000 psi, Young's modulus 30 million psi, and Poisson's ratio 0.3. We're given some info about this area here, and then we have our answer choices. Then immediately after reading the question, we're going to write what we're solving for and its units. So we're solving for an F, and the assumption here is pounds force. Okay, great. So let's take a look at this in a little deeper analysis here. So here's our strap, and it's looped around the hook, and the force is pointing straight down. We're given some info about this area here, and the assumption here is that this hook is 1 inch deep or 1 inch in thickness, and this is a top-down view of this interface, 1 inch by 1 inch. Okay, let's get to it. First step, is we're going to draw a free body diagram. All right, so I've got just the hook here. Now, our component is 3 pieces, 1, 2, and 3. But I told you this is probably going to be something tricky, so let's think about this for a second. I chose the hook here because that's where the force is applied. So if I've got a force which is dead in the middle of the center line, that's what this dashed line is here for, that shows us that we've got a force that's off center from where this hook is pinned. So as the F pulls down, the hook's going to want to try to rotate. So there's a force coming from the latch or applied from the latch that's forcing the F back to the center line. That's why this is self-locking. So I've selected the hook here to draw my free body diagram with. And we're going to just start simple. We know how to do pin reactions, so we've got a force in the Y direction, and we've got a force in the X direction. Now, I'm going to take this, make an assumption here, and take this strap, and I'm going to apply this force straight down. As long as it's in the center line, I don't think we have any troubles. All right, and then we've got uniformly distributed load here. Why do I say that? Well, assume uniform pressure distribution at the latch mating face. Okay, that tells me that in this interface, I've got an uniformly distributed load. I'm going to rewrite that, though, as a resultant, dead center of the middle of that uniformly distributed load, and I'm going to call it R. So I've got 4 forces, or 4 unknowns, 1, 2, 3, 4. Let's jump straight into our equilibrium equations. First thing I'm going to write is the sum of moments. About point 0, I'm calling this point 0. This is my positive direction. I've got R times dr plus F times dF. What's dr? Okay, so I've got my center line here and my radius here, but I'm summing moments about this point, so my dr is this distance. And what is that value? Let's look back at our question again. Outside radius of this hook is 3, inside radius is 2. And the offset from center line to my pin is 1/2 inch. So 2.5 inches minus 0.5 inches equals 2 inches. This is 2.5, this is 0.5, so I get 2 inches. dF, straightforward. That's this distance, which is given in the problem statement or problem diagram, 1/2 inch. Okay. Now I can also write so my Fy here, positive Fy minus negative R, or minus R minus F equals 0, equals 0. Doesn't tell me anything, really no help here. And sum of Fx equals 0. No help here. So I'm a little bit stuck. This is where the multiple step problem component comes in. Well, I need a 4th equation to help me here. Got a couple keys here, clues here in the problem statement, though. What is the maximum F the hook can handle before plastic deformation occurs at the latch mating face? And if I've got uniform pressure distribution, that tells me that I've got an axial stress problem over this interface. So my generic axial stress formula is sigma equals force over area. So I'm going to rewrite that for specifically what we're dealing with here. The yield stress of the hook material is equal to R over A. I'm just going to call this area A. And again, we've got some info from the problem. Hook and latch are made from a material with yield stress 52,000 psi. Anything over that, I'm going to get plastic deformation, so that's a giveaway. I'll just rewrite that here. So 52,000 psi is equal to R, my unknown, over A. What's my A? Well, they gave it to us, thankfully, 1 inch by 1 inch, 1 inch squared. That was a gimme. Thank you, test authors, 1 inch squared. So now I can rewrite this and solve for R. R equals 52,000 psi over 1 inch squared. Well, that just equals 52,000 pounds force. Great. That's good. So we've used an outside non-statics equation to give us one of our unknowns. Let's rewrite some of the moments about zero, about moment, or about 0.0. RdR minus F dF. Let's put some numbers to it. 52,000 pounds force times 2 inches minus F, half an inch. I'm going to rewrite that, solving for F. Let's see, that equals 0, excuse me. 52,000 pounds force, 2 inches, 0.5 inches, equals, RF equals 208,000 pounds. Okay, that's it. Let's check. Do we have this as an exam or as a choice? We do. Good, got it. All right, that's it. But let's talk about it a little bit. Why, when you look back at the steps we took, it really was fairly simple. And I think that's going to be true for most machine component statics problems. We really only needed one equilibrium equation. But what made it a complicated multi-step problem was a couple things. First off, you needed to know that this was A, a uniformly distributed load, and B, that you could resolve that into one single resultant. The next thing you needed to know was, well, we've got an axial stress problem, and that this is referring to a 1 inch deep area here. So you had to know, okay, I need to use this guy. That's important. You also needed to know, I don't need to know Young's modulus and Poisson's ratio. Also, I didn't need that or that. So excess information, sorting through, man, I got to throw out the bones, keep the meat. We have a tricky component here. I had the first time I saw one of these self-locking hooks, I had to stare at it for a while. It's kind of weird how it works. We also had to know which of these three components to do our free body diagram on. So see, there were probably 4 or 5 decisions that we needed to make quickly and to know our statics really well before we could really get to the problem. Once we got to the problem, I mean, it was really 3 equations and we were done. So I think this is a good example of what you're probably going to see, or a good example of a machine design component that's on the equivalent difficulty of this test. But that's it, guys. That's all there is to it. Remember, you don't have to be a genius to pass this exam. We'll see you next time.